So let's get started. So it's we're in segment 5 of module 4. In this module again, because segment 4 was a little bit on the longer side, I'm going to just limit it to segment 5. So hopefully it's a short segment. So what we're going to do today is we're going to introduce a very beautiful random graph model, the Erdős-Rényi model. It's very, very simple, and that's probably why it's so beautiful, and leads to a lot of interesting things. In particular, there's this notion called phase transition. We'll define that, and we'll show at least one phase transition. Okay, and so let's, without further ado, let's get started with the definition of the Erdős-Rényi graph model. So it's a little bit of history. So this paper was published probably in the early 60s, and since then this model has really gotten the attention of people. Lots of very pretty results have been proved. Basically, what is this? The it's a graph denoted by, it's a random graph. So it's essentially what it is a probability space. We're denoting that by G and P. It's the probability space over all graphs with n labeled vertices. Okay, and if it's a probability space, then there must be a probability function associated with it. How do you get the probability function? In some sense, implicitly, for each pair of vertices in you create an edge with probability p. So that accounts for the two parameters that show up in the notation. It's G n p. N is the number of vertices. P is the probability with which any pair of vertices you see will have an edge. Okay. So now one way to think about it is you create the n vertices, and for each pair you toss a biased coin with probability p, and if it shows up heads, put an edge between them. Otherwise, move on to the next pair. Okay, and these are all independently chosen, of course. So it's a very elegant, simple way to define a random graph. Okay, and actually closer to what Erdős-Rényi originally defined is this notion called G and M. Okay, in this case, this is actually very close. These two are very closely related. G and M is again a probability space, again over all n vertex graphs, but now you choose m edges at random from uniformly at random from all n choose two possible vertices edges. Okay, and these are essentially similar. If you set up the probability p to be, well, if you set up the probability p to be equal to m over n choose 2, then essentially both will be about the same. Okay, they're not exactly the same, but about the same. Okay, our focus, of course, will be only on G and P. Okay, and we introduce a notation G and P models P. Okay, or has the property P. It denotes the event that a random graph drawn from this distribution, this probability space, has the property P. And what is the property P? It could be any graph theoretic property. Graph is connected or bipartite or has a clique of size 4 or whatever. Any property, we can ask, does a graph drawn from this probability space have that property or not? That's whether it has the property or not is the event, and then you can talk about the probability of that event. Okay, and what do we mean by threshold? Phase transitions. If a property has this nice threshold function, okay, some function such that when p, the probability with which edges are chosen, if p is just less than the threshold function, then the probability that you see that property tends towards 0, okay, which means most likely you don't have that property when the p is just less than the threshold. But then when you when you raise the probability just above the threshold, then immediately the probability that you see that property skyrockets towards the almost always there probability. Okay, that is probability 1. Right. So, this is the phase transition. So, when you can come up with such a threshold function, then we say that you experience a phase transition at that threshold function. Okay. So, today what we are going to do is study the one such phase transition. So, we are going to look at the phase transition for the property that property P that says that the graph has a clique of size 4. Okay. In other words, way to think about it is when your probabilities are very, very small and you create this graph on n vertices, when the p value is very, very small, you do not see cliques of size 4. You may see cliques of smaller size, but it is very difficult to see cliques of size 4. But then when you just increase it beyond the threshold, you suddenly start to see cliques of size 4. And as soon as in particular here the threshold function is n to the minus 2 by 3. Okay. When you set the probability to be little o of n to the minus 2 by 3, then the probability of seeing cliques of size 4 tends towards 0, and otherwise the moment you say that the probability of having edges is little omega of n to the minus 2 by 3, then immediately the probability that you see that property tends towards 1. Okay. Okay, so let us see how we can prove this theorem. The first claim is reasonably straightforward. So, this first claim is when the probability is less than or not technically little o of n to the minus 2 by 3, we want to be able to say that you do not see cliques of size 4. Okay. So, how do we do that? Well, let us start by listing the cliques, all possible cliques. There are n choose 4 possible cliques, right. So, you list them one by one in some arbitrary order. Okay. And you we are finally going to shoot for the number of such cliques that get formed. In particular, we want what we are finally shooting for is the probability that x equal to 0. We want to understand what is the probability that you do not see cliques, right. But towards that, what we are going to do is we are going to set up the variables so that this x can be broken into these xi's. Xi is 1 if the ith Ci is a 4 clique and a 0 otherwise. Okay. It is an indicative random variable. So, clearly now the number of 4 cliques is given by uppercase X, which is a summation of all these individual Xi's. Okay. And you notice that X is integral, it is an integer, and X is always going to be greater than 0. So, now we can ask the question, what is the probability that X is greater than or equal to 1? We want to argue that this probability becomes very small, little o of 1. So, what is the probability that X is greater than or equal to 1? First of all, we claim that this is less than or equal to the expectation of X. Why is that? Okay, so I was thinking of a slightly different way to do this, but yes, you can do this way. I had a slightly different idea, but that's picked up another way to see this. Okay, great. So, by Markovs, let us even put it that way. All right. Okay, so then what do we do? So, this is at most expectation of x. So, we need to bound the expectation of x. Actually, we can get the exact value of expectation of x because first of all there are n choose 4 such indicator random variables. Okay. So, that is and each one of them is 1 with probability p to the 6. Why is p to the 6 showing up here? Yeah, because you are talking about 4 vertices and you are asking whether all of them have all pairs are connected by edges, and so you will have 6 edges, and so that is why you have p to the 6. Okay. And we know in this case we are in the case where p value is little o of n to the minus 2 by 3. Okay. And p is raised to the power 6. So, you get n choose 4 times little o of n to the minus 12 by 3, and n choose 4 is o of n to the 4, and then but this term is little o of n to the this is what n to the minus 4. So, overall it is little o of 1. Convinced about that? Okay. Okay. So, the first case was nice and easy. Okay. So, let us look at the second case. So, this is the case where the threshold function, I mean this probability function is little omega of n to the minus 2 by 3. So, it is more than n to the minus 2 by 3. Okay. And in this case we want to show that the probability with which the property will hold is tending towards 1. Okay. Remember, epsilon is a very small quantity. In fact, for any small epsilon we want to be able to prove that it is greater than 1 minus epsilon. Right. Another way to prove this is just the opposite, the probability that x equal to 0 is at most epsilon. Okay, this is the case where you do not see any 4 click, in some sense the bad event in this context. The bad event is happening with less than epsilon probability. Okay. So, let us see. So, now here let us look at the expectation of x. In this case, remember, p value is little omega of n to the minus 2 by 3. So, when you plug it into that formula, remember we said n choose 4 times the expectation of each individual xi's, you get this quantity. See, this is n to the 4, and this is going to be little omega of n to the minus 4. Okay. So, overall it is going to be tending towards infinity. Okay. And so, this seems promising. Why? Because now what we are able to see is that the expectation of x is tending towards infinity, which means that this x equal to 0 intuitively is an unlikely event. Okay. But that is not sufficient technically, because we want to be able to show that x equal to 0 with we want to be precise about this. We want to show that the probability that x equal to 0 is at most epsilon. So, one thing that why is this not sufficient? Let me ask you this, why is this not sufficient? Why is this not sufficient? You could have situations where the expectation is very large, because let us say for example a situation where x takes the value either 0 or a very large value. Okay. 0 with some probability, say half, and this very large value with or rather let us say 0 with probability epsilon, and some very large value with probability 1 minus epsilon. Okay. And if this large value tends towards infinity, then itself you will get expectation of x to going to infinity, but that will not satisfy this requirement that you have. Okay. So, that is why we need to be a bit careful here, and this is where it connects to tail bounds. Remember, we are in the context of tail bounds, we are trying to understand applications of tail bounds. We need a new trick, we need a tail bound based trick, and what we are going to see is what is called the second moment method, and we are actually going to apply Chebyshev's, but in fact we are just going to rewrite Chebyshev's in the manner that we want, and then we will try to apply it. So, now we are going to assume that x is a non-negative integer integer random variable, and we want probability that x equal to 0, and this is exactly what we wanted over here. Okay. And this probability that x equal to 0 is at most the second moment method uses this inequality, that it is at most variance of x divided by expectation of x the whole squared. And it is actually coming from a very straightforward application of Chebyshev's. So, what is x equal to the probability of x equal to 0? You can write this. So, what is this? So, now you want to know what is the probability that x equal to 0, and let us say this is the expectation of x. What Chebyshev tells you is it bounds both of them. Okay. This is the 0 mark. So, it bounds x minus e of x greater than or equal to some parameter a, right. In this case, that parameter is nothing but e of x itself, right. So, in here this is also e of x here. Okay. So, you can basically write this x equal to 0 event as well, it is basically x equal to 0 will be a subset of this event that says the absolute value of x minus e of x is greater than or equal to e of x. Okay. And then you apply Chebyshev's inequality and you get. In our context, so going back to, we want to be able to say that this is in little o of 1. Okay. We want to show that this is little o of 1. Basically, now what we need to show is that the variance of x is little o of expectation of x. So, if we show that, this whole thing will fall into place. So, this is going to be our focus from now on. So, now we need to understand the variance, for which let us try to bound the variance when we have a certain property. We have this property that this x is the summation of 0, 1 random variables. Okay. If that is the case, well, it obviously looks very similar to the variance formula that we already are familiar with. So, we just need to do some minor massaging. Okay. So, we know that variance of x is the summation of the individual variances plus these covariance terms. Okay. The covariance terms is already matching what we have over here. So, we do not worry about that. So, we only worry about the sum over all the individual variance terms. Okay. And well, then you can just apply the formula. Variance of x I is expectation of x I squared minus expectation of x I the whole squared. That is just the formula. Okay. But now we are going to take advantage of the fact that x I is a 0, 1 random variable. If it is a 0, 1 random variable, e of x I squared, what is that? It is going to be 1 squared with probability p and 0 squared with probability 1 minus p. Okay. And that is nothing, this 1 square does not, it again shows up as 1, and so it is again just p, right. So, this is nothing but expectation of x I, and here we want an inequality. So, and this is a positive quantity. So, we simply can ignore it. We want the less than or equal to over here. Okay. So, it is nothing but expect sum over all I x I, okay, which by linearity of expectation is the expectation of this big random variable x plus the covariance terms. Okay. So, this is what we have. So, now we have a way to bound the covariance. So, we will just go ahead and bound it. Okay. So, now we need to, just to recall, we want to show that the probability of x is equal to 0 is at most epsilon, and we are applying the second moment method, and we have a way to bound the variance, which is what is written over here. Okay. Expectation of x plus all the summation of all the covariance terms. Now, if you look at so a few things that we need to worry about here. So, we need to worry about the covariance terms now, and in the denominator we have an expectation of x the whole squared. Okay. So, if you think about it, if you recall, we want to show that variance is, what did we want to show? We want to show that variance is little o of E of x squared, right. So, this is not going to be too much of a problem. It is the covariance terms that we need to be careful about now. Okay. But anyway, let us go through all these terms, and just to recall, the covariance has this formula: covariance of xi and xj is expectation of xi xj minus the product of the individual expectations. We have that formula, and we already know the expectation of x. So, this expectation of x the whole squared is going to work out to n to the 8 p to the 12. Okay. That is just by applying the formula. Okay, so let us now focus on the covariance terms. So, now we are going to focus on the covariance terms, and for the covariance we need to be a bit careful, because remember, this covariance is is over all pairs, ij pairs, right, and funny things can happen. So, let us break it down into cases. The first, or sub cases rather, sub case, what let us see, the first sub case is this C I intersecting C j is either the cardinality is either 0 or 1, okay. And I claim that this is the easy case where all the covariance terms are zeros. Why is that? Independent or same? No, we need to be, they are just independent. Why are they independent? So, let us look at them one by one. What is C I intersecting C j, the cardinality equal to 0? What is that situation? Yeah, the cliques are completely disjoint. There is one and then the other one. Okay. What happens in one set of 4 vertices will have no bearing on the other set of 4 vertices. What about cardinality of C I intersecting C j equal to 1? What does the picture look like? What will we have to do to this picture? Yeah, one of the vertices is common, right. So, basically let us remove each. So, now we are asking, are these 4 forming a clique and are these 4 forming a clique? Okay. And why are these still independent? Yeah, so the vertex, one vertex might be common, but the edges are all chosen independently. So, because this edge, whether this edge is chosen or not, has no bearing on whether this edge is chosen or not. Okay. So, even though there is a common vertex, the whether the cliques are formed or not are independent events. So, the covariance terms for those cases are 0. What about the case where C I intersecting C j equal to 2? So, let us draw the picture for it. So, we have 2 common vertices, and then the rest of the vertices will look like this. So, we are asking, are these going to form a clique and are these going to form a clique? Okay. So, now there is essentially just one edge that is common. So, now you start to see some amount of independence showing up, sorry, dependence. So, now we are going to claim covariance is upper bounded by p to the 11. Why is that? Well, for one thing, we want an upper bound, so we are going to ignore this this term. Okay. We only have to worry about E of xi times xj. So, now what we want, what is that? That is the expectation. I mean, that what is xi times xj? It will be 1 when both the cliques are formed and 0 otherwise. How do you get to form both the cliques? How many edges should actually get formed? If you look at the 2 cliques as separate, how many? It is a total of 12, but one of those edges is common. So, you need to form 11 edges, that is p to the 11. Okay. So, that is So, those that will be the covariance term for this case where there is one common edge. A very similar argument can be used for the case where 3 common vertices. When there are 3 common vertices, let's draw the picture. So, you 3 common vertices, and we are asking, okay, are these forming a clique and are these forming a clique? Okay. So, now there will be 1, 2, 3 common edges, and then 1, 2, 3, 4, 5, 6. So, there will be 6 other edges, a total of 9 edges. So, we have p to the. So, now we have the covariance terms individually. So, we just need to put them into the summation. Okay. So, recall that this is the covariance that we want to compute, so variance that we want to compute. This expectation of x is this term, n choose 4 p to the 6, we have already seen that. Whenever Ci and Cj have an intersection of either 0 or 1 elements, we have just discarded them. So, we only have to worry about the case where they have 2 common vertices or 3 common vertices. So, this is the case where they have 2 common vertices. Okay. You may recall that when they had 2 common vertices, the covariance itself was p to the 11. But how many such covariance terms will be there? That's going to be the number of ways in which you can choose these 4 vertices for the first clique, 4 vertices for the second clique, such that they have 2 common vertices. Okay. How do you count that? First of all, you need to remember the picture. You need to first get 6 vertices. Okay. After you get 6 vertices, then you have to choose 2 of them to be the common vertices. So, this is choosing the 6 vertices. Then out of those 6 vertices, you want 2 to be in the middle. Then you want to choose 2 to be here, and then you want, of course, the remaining 2 will go here. Okay. That is the number of such covariance terms that you will have. So, you get that, and a similar argument can be made for this one. So, here again, if you recall the picture, okay, 3 common vertices. So, out of the n vertices, you choose 5 vertices, okay, and out of those 5, 3 of them go in the middle, okay, and then 1 on the left, 1 on the right. All right. So, now what we do is let us plug in the terms. So, in the interest of time, what I am going to do is just point out. So, remember that p is we need to be a bit careful here. Okay. So, let us for the moment just ignore this line. Okay. So, let me see. Now, let us just write these things in terms of n and p. So, here this is going to be an n to the 4 p to the 6, and that is clearly little o of n to the 8 p to the 12. Then this is going to be an n to the 6 p to the 11, again little o of n to the 8 p to the 12. This is going to be an n to the 5 p to the 9, again little o of n to the 8 p to the 12. So, you get little o of expectation of x the whole square, which is exactly what we wanted to show. Okay. So, that really brings us to the end of this segment, because what we have shown with this, we have shown that the probability, going back, probability x equal to 0 is less than epsilon for any arbitrarily small epsilon. So, that is exactly what we wanted to show and completes all the cases. Well, let me conclude. So, what we have introduced is random graphs, defined transitions, and we have shown one phase transition. And we have shown along the way we learned a nice method called the second moment method. In the next module, which we will do after in this classroom setting, we will be doing this after our first quiz. We will go into things like balls into bins and some other computer science applications of that. Okay. So, thank you. Some easy questions first. So, look at this random graph g n comma half. Okay. Okay. So, here I want you to argue two things. One is argue that every vertex has more than minus epsilon times n incident edges with high probability, of course. Should be very easy. And the second thing I want you to prove in this is prove that with high probability diameter of this is at most 2. Okay. Couple of things that you should be able to prove quite easily. The other thing is that for this is for arbitrary p, f of n equal to log n over n. Prove that this is a threshold function for connectivity, for the property that the graph is connected. Okay. So, some interesting problems to work on. In the 10 minutes you should be able to do this.